Right, so what we want to start looking at now is the difference between homologous and analogous structures. I said to you just now that who's the one who is basically looking at the bones and trying to determine, is this species related to that species? Maybe they have a common ancestor, or you might look at things and go, these structures are completely different and therefore there's no relationship between them. That brings us to homologous and analogous structures. Now remember, homo means same, so therefore a homologous structure is where we look at structures that might even perform different functions today, but because they have similarities in the structure, we would say that they came from a common ancestor and are therefore homologous.
Would that be like the pancreas or something in the human body?
Are you thinking of the vestigial organ, the appendix?
Appendix,
I'm coming to the... That's an organ. That's a good question, because we're coming to that just now about how some things were functional in an organism and are now no longer functional.
Okay.
So we're going to come to that. So if we are dealing with common structures in terms of bones, we would say that these organisms might be related. If, on the other hand, we look at analogous structures, that would mean they're not related. Let me deal with homologous first, and then we'll come to the analogous in a moment. So this question over here shows us the basic plans of different vertebrate limbs. We can see we have the generalized forearm of the mammal over there. We have the bat, which is, of course, designed to form a wing. And there we have the forearm, of course, of the mole. Now, even though we can clearly see differences, if I come over here, if I look at our forearm with a long humerus, ulnar radius, and our phalanges over there, which are our fingers, which are there designed for picking up things, moving things around, for using tools and these sorts of things. If I look here at my bat, I still see, look what I've got here, a humerus, ulnar radius. But in this particular case, the finger bones, or the phalanges, have become very long, thin, and light. Oh, I'm putting my head in the way. We have these long phalanges over there, and these phalanges are, of course, got membranes in between them, and it is therefore designed as a wing. If we look at our mole, for example, once again, humerus, ulnar, radius. Here are the carpals, the wrist bones over there, and then, of course, these phalanges have become short and thick and strong and are therefore designed for, of course, digging. But remember, we can clearly see that if we look at all of these bones, they are all very, very similar in structure. So I've looked at my resource and I'm immediately thinking to myself that I am dealing with homologous structures. So let's come to these questions. Number one, are the above examples homologous or analogous? Homologous, homo, same. Explain your answer to the above question. Remember, as we said before, even though the bat's forelimb is for flying, the mole's forelimb is short and thick for digging, ours, as we said, is used for tools and these sorts of things, because they have the same or very similar bone structures, we would say they're homologous. They came from a common ancestor. Homo, same, the same ancestor, that they are all related in that particular way. State one way in which the forelimbs of the bat are adapted for flying. As we said, if we come over here, long, thin phalanges with a membrane in between, therefore it's for flying. How is the mole adapted for digging? As we said, very short, thick claws in our mole, and therefore it is designed, of course, for digging holes. But what I want to do before I go into the next question is talk about analogous structures. So we can clearly see we know what homologous structures are. Similarities, therefore, we'd say that they came from a common ancestor. What does analogous mean? It means we're looking at structures that perform exactly the same function, but there is absolutely no relationship in terms of their structure. Wow. Let me give you an example of this. If you think of the bat of a wing, the bat of a wing. The wing of a bat, as we were just looking at now. If you think of the wing of a bird, and a bird, remember, is descended from the dinosaurs, those reptiles. And if you, for example, look at the wing of a butterfly, which is an insect, all three of those structures are well designed for the purpose of flight. But if you look at them, there is no similarity in the structure itself of those three different wings, and it is therefore they are said to be analogous. There is no common ancestor that exists between them.
Okay.
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 Right, so if we look at the next one, it says, here is your thing about vestigial organs. It says, Darwin said in his book, organs or parts which seem useless are very common in nature. In many snakes, there are small bones of the pelvis and hind limbs. And here we look at the diagram below, shows the vestigial or reduced pelvis and femur of the whale. Before I do this, I want to come back to what you were asking me, Addo. We have an appendix. Now, an appendix is part of our large intestine, or, well, basically where the small and the large intestines join. And it is said that that appendix was once a part of like the rumen of a cow, where the bacteria lived in there, and they used to break down grass. But now, as we became less and less dependent purely on plant vegetation, and our digestive systems became more advanced, we no longer needed that anymore. Wow. It's still there, however, but it's not serving any function, and that means it is a vestigial organ.
Okay.
Okay, and here we're looking at a whale, the back of a whale. And what you can see, if you look at this back of the whale, that here is the spine bone over there, and even though there are no hind limbs in the whale, we can clearly see that there is the reduced pelvis, the reduced femur bones, etc. What are they there for? They're not serving any function. They are a vestigial organ. So let's look at the questions. In terms of natural selection, which we're talking about all the time, explain how the pelvis and femur that were once useful to the whale's ancestor could have become vestigial in modern whales. Now, what is interesting, we say that all life evolved in water. Some organisms then came out of the water, and basically what is said that some went from terrestrial back into the water. And the whale is an example of one of those. It's said that the whale developed from a four-limbed terrestrial organ or an terrestrial mammal, and then moved back into the water.
Wow.
And that those who already had smaller hind limbs may have been better able to swim, might have been, you know, less sort of sluggish in the water, might have been better able to capture food, those sorts of things. Mm-hmm. And therefore, those that were living in the water, those with the smaller limbs, catching food, better able to swim, etc., survived. Those with the bigger sluggish limbs maybe were better able to adapt at catching food, maybe also were hunted because they were sluggish, maybe they were captured by predators more, and therefore they died. And that is why we would have by natural selection, we would have a slow disintegration of that pelvic girdle in the whale.
It makes sense.
Okay, and then it says suggest one reason why a vestigial structure, once it has been reduced to a certain size, may not disappear altogether. Well, that's a very relevant question.
I was thinking about that. Why
does
do
it
we
just
still
disappear?
have the appendix?
Why do we still have an appendix? Good, because it is said that when it's not something's not selected for or against, and the gene is still there, that the structure will still manifest itself. Okay. So the gene is still there, but of course we know that it's just getting expressed in a very small way. And that, of course, that because it's not selected for or against, it's not going bigger or smaller.
It just stays the same.